Record. Okay, so we're going to go through a bit more proof today. I'm going to sort of talk about all the different overviews of proof that you'll do, and then we go over the proof by deduction that we started looking at on Friday, and we'll look at proof by counterexample and proof by exhaustion today. Eventually, when you go into the second year of A-levels, you will also do proof by contradiction, but we don't need to do that yet. And then further maths is also proof by induction, but again, that's not something we need to look at right now. So summary of types of proof. So Friday we did proof by deduction. Sometimes people call it direct proof as well. So this is where we use logical arguments to show that something must be true. So for example, we were saying that I can't actually remember, two even numbers, if you add them together, I think that's what we were saying anyway, if you sum two even numbers together, you'll always get an even number. And so we were using logical arguments to show that that is always true every time. Today, we're also going to recap that. We're going to look at disproof by counterexample. So this is where we find where the claim is not true. So we actually disprove the comment. So you can get given a conjecture, and you need to say, actually, no, this isn't true because X, Y, and Z, these don't match. And then proof by exhaustion. So breaking the claim down into two or more cases and showing that it is true for every case under consideration. So counterexample and deduction are your slightly easy ones. Proof by exhaustion is a little bit more complicated. I'm also going to show you, if I can get it to work, how to make a table on some of the calculators to help you with proof. I'm saying if I can get it to work because I'm not 100% sure if it will show over Zoom, but we'll try. So disproof by counterexample. I'm actually going to skip this for a second. I'm going to come back to that in a minute. I want to go back to proof by deduction. So another recap of proof by deduction that we did on Friday. So proof by deduction. So for example, you could be asked to prove that the sum of every positive number and its reciprocal is at least 2. So that's your conjecture. So basically, we want to show that n plus 1 over n is greater or equal to 2. And for n, our number, to be greater than 0. So our number n has to be greater than 0. And so we're saying that n plus 1 over n and its reciprocal is at least 2. So what we do here, so this is basically a disguised quadratic equation. So what we need to do first is we need to multiply through by n. So we need to multiply both sides through by n. So we end up to get rid of our 1 over n. So we have n squared plus 1 gives us a number that is greater to or equal to 2n, which we know should be right, 2n, because we're saying our number is going to be at least 2. Oh, and then we've got another one of our symbols from the day. So therefore symbol, 2n minus, n squared minus 2n plus 1 gives us a number that is greater to or equal than, or equals to 0. So you can see we're basically working through a quadratic equation here. So then we're going to factorize the quadratic. So then we'll go in with adding in our brackets. So we'll have n minus 1 squared, and any square is greater than 0. So therefore, n minus 1 squared greater than 0 is true. So the point is, basically, we're working through this quadratic equation to get to the point where we can prove that actually it's always going to be 2. So the sum of every positive number and its reciprocal is at least 2. Okay, well, n, and so we're going to say n is going to be greater than 0 every time. So for any square is always greater than 0. So therefore, n minus 1 squared is always going to be greater than 0. So that is true. So n plus 1 over n is greater or equals to 2, provided that n is greater than 0. So basically we have a caveat in there, we have a rule in there saying, which was in our original equation, so we want to show that n plus 1n, so we said every positive number. So obviously if we were dealing with negative numbers, this wouldn't necessarily be true, but in our question we've clearly stated up at the top that it's the sum of a positive number and its reciprocal. So therefore we're just talking about positive numbers, so n has to be greater than 0. So therefore n plus 1 over n is greater than or equals to 2, provided that n is always a number greater than 0. Some people do occasionally like to conclude proof. So like I was saying, that proof is like writing a story, and we're having all of our steps written down as we're going. Sometimes people like to actually conclude their proof with QED. QED is short for Latin quod erat demonstrandum, which basically means, so I've shown what was required. So this is what was required. Here we go. This is the answer. It's almost like putting equals. So this is the answer. So some people like to put that at the end. So if you see any textbooks or any examples with QED at the end, that is why. So here's another proof by deduction. Example 2. We're going to prove that every positive 2-digit number is greater than the product of its digit. So for example 23, so if this is a positive 2-digit number, 23, 2 times 3 equals 6. 9 times 91, 9 times 1 equals 9. So it's true for these, but there are 92-digit numbers. And basically what you're not going to want to do in an exam is sit there and work it out for all of the 90 numbers. It's not a good use of your time. It would also take a long time, and it's just silly. So we have to basically then look at a different formula. Well, actually, how can we find this out in a more sensible way rather than sitting here and doing 90 sets of multiplications? So we're going to use some algebra to help us. So we're going to call our tens digits A and our unit digits B. So 1 is less than or greater to A, and A is less than or equals to 9. So basically we're saying A is a number between 1 and 9, and B is a number between 0 and 9. So B, 0 is greater than or equals to B, and B is greater than or equals, is less than or equals to 9. So we need to multiply A by 10 to put it into our tens column. So our 2-digit number will be 10A plus B, because obviously we're talking about a 2-digit number. So to multiply A by 10, to put it in our tens column. And the product of the digits is AB. So we want to show that 10A plus B equals AB. So we're going to rearrange our statement. So we've now got 10A minus AB equals minus B. Since 0 is less than B and B is less than 9 or equal to 9, minus B must be negative or it must be 0. So we want to factorize this now. So our next step is factorization. So we're going to factorize this. So we have got, when we factorize it, we're going to end up with A brackets 10 minus B. So 10 minus B multiplied by A will give us minus B. A is positive, okay? And since B is a less than 10, 10 minus B must also be a positive number, okay? So the left-hand side must be positive, as it's a product of 2 positive numbers. And since we know that the right-hand side is 0 or lower, the inequality is true. So if A 10 minus B equals minus B, it's true then that its rearrangement 10A plus B goes to AB must also be true. So the statement, every positive 2-digit number is greater than the product of its digits, is proven to be true. So we've basically used our algebra and quadratics and factorizing equations to go in here and basically prove that every 2-digit number is greater than the product of its digits in a way that is quicker and easier than going through and doing 9 times 1 is 90, 9 times 2, 9 times 1 is 9, sorry, 9 times 2 is 18 and just spending a whole lot of time working through that. So we've gone through all the different steps there to try and do those proofs by deduction. So some useful points to remember for when we do proof by deduction. If n is any integer, then 2n represents any even number, and 2n plus 1 represents any odd number. So we did that the other day when we were talking about when we're using different annotations. So n is our integer, 2n is an even number, 2n plus 1 is an odd number. If we need to use two unrelated numbers, then we call them, for example, m and n. So they're numbers if we don't know what their relationship is to each other. So three consecutive integers, we did this the other day, can be written as n minus 1, n, and n plus 1. You could also use n, n plus 1, and n plus 2. But the reason that we use a former is it may give terms that cancel out more neatly. So n minus 1, n, and n plus 1, if we're then going to want to cancel out terms, using that is a lot easier and neater than n, n plus 1, and n plus 2. But you can use either. They are both technically correct. Just the first one would necessarily be a little bit easier. If you can take out a common factor, then the expression must be a multiple of that factor. So for example, if n is an integer, then 3n squared plus 6 equals 3 brackets 3 lots of n squared plus 2. Therefore, it must be a multiple of 3. Okay, so our n, if it's an integer, if we take out the common factor, the expression must be a multiple of that factor. So it must be a multiple of 3. A rational number can always be written as a fraction. So for example, a over b, where a and b are both integers and b does not equal 0. So I'm going to put these examples on here, and I want you to pause this at some point later when you watch this again and have a go at these examples. I'm just going to talk them through with you now to have a go at these proofs. So using the proofs that we did on Friday and the examples of proof by deduction I've just re-gone over and these useful points, I want you to have a go at trying these 5 examples. So first of all, prove that the sum of any 3 consecutive integers is divisible by 3. 2, prove that the sum of the squares of any 2 consecutive integers is odd. 3, prove that the sum of 2 rational numbers is also a rational number. 4, prove that the product of 2 odd numbers is always odd. And then finally 5, if the perimeter of a square is the same as the circumference of a circle, then prove that the area of the circle is greater than the area of the square by a factor of 4 over pi. And I'm not going to go through, I'm not going to go through them now. So yeah, pause them, have a go at them, and then if you have any questions about them, let me know, and then next time we do some maths we can go through them now. So I'm not going to spend the time going through the answers now because we've done lots of examples of answers. These are some for you to just have a go at by yourself. Proof by deduction. What's wrong with this proof that 2 equals 1? Okay, so if we were going to do this, we would have a equals b. Therefore, a squared equals ab. So if a squared equals ab, therefore a squared minus b squared equals ab minus b squared. So that would then, if we factorize that, we have a plus b multiplied by a minus b equaling b multiplied by a minus b. Therefore, we get a plus b equals b, a plus a equals a, 2a equals a, 2 equals 1. So what is happening in each step? Okay, so we've got definition. We're going to define what's happened. We've multiplied both sides by a. We subtracted b squared from both sides. We factorized. We've divided both sides by a minus b. We've substituted a for b. We've gathered like terms, and we've divided both sides by a. So we get 2 equals 1. Where is the error? So there is an error in here. what you can do is, if you're doing this yourself later, is you can pause, try and work out the error, and then I'm going to explain where the error is now. So obviously it's not in our definition point. A equals B is correct. We've multiplied both sides by A. That is correct. Actually, in step 5, we have the issue. So step 5, we're supposed to have divided both sides by A minus B. That is where the error is, because dividing by A minus B means dividing by 0, and we can't do that. So A minus B would give us 0, and we can't divide by 0, so we can't do that. So the error is at step 5. We're not going to do proof by exhaustion yet, so we're going to go back to here, and we're going to go through disproof by counter example. Disproof by counter example is basically we're just saying, no, this is wrong. I can show you this is wrong because here's an example of why it's wrong. So you might get asked, you might get the conjecture, disprove the statement that for any pairs of integers, x and y, if x is greater than y, then x squared plus x is greater than y squared plus y. So we need to find a counterexample. So basically what we need to do is we need to find a pair of values for x and y for which the statement is not true. What's really important here is actually in our conjecture, for any pairs of integers, we are not getting told that they're positive integers or negative integers. So we've got the whole range of integers to work with here. So we could try some examples. So we've said, okay, x equals 2, y equals 1. So x squared plus x equals 2 squared plus 2 equals 6. So y equals 1. So y squared plus y equals 1 squared plus 1 equals 2. So 6 is greater than 2. Okay, yeah, no, that's true. So we can't disprove it with that one. So then we would have to find another set of numbers. And obviously, we've got a huge amount of numbers that we could deal with here. So we can't just sit here and just go through exhausting every single set of numbers. It just wouldn't be a viable way. So this statement is true in this case, and it actually looks like this would apply for all pairs of positive values. So no matter what our positive value is, as long as x is larger than y, then x squared plus x will be greater than y squared plus y. However, we haven't looked at negative values, so we could look at negative values. If a counterexample doesn't jump out at you straight away, then it might be helpful to use a table function on your calculator. This is where I'm going to try and show you how to use a table function on your calculator, which I don't know if it's going to work. Let's have a look. Menu. Table. Oh. So we are nearly there. So F. So on our table, we've got fx. So x in this situation is going to be -4. Enter that, and our g would be 12. Start, end, start, repeat, enter, and then we get a table being brought up. So basically what we could do is we can look at the different ways that we can compare them on the table. I don't actually know if you could see any of that. If you can't see any of that, I was just talking nonsense, so don't worry. I will try and find a better way of showing you how to do that on a calculator. So basically, if you can't see a counterexample, jump straight out at you. You use the table function on your calculator. So in this case, we find x squared plus x for a range of values of x. So we could say our range of values for x could be from -4 all the way up to +4. So we might just use them as an example. Let's see if I can actually get this up at the same time. So we should eventually end up with a table that looks like this. So we have x and being -4 all the way up to 4, and then we would put in x squared plus x, and this would come up as a table on your calculator. I've never used one on the computer before, and it's very strange trying to use it on a computer rather than on an actual calculator. So I might try and film my calculator next time to show you how to do it actually on a calculator. So for example, now we've got, if x equals -4, we've got 12, x equals -3, 6, x equals -2, 2, x equals -1, 0, x equals 0, 0. So we've got the whole values here. So if we choose, for example, x equals 1, and we choose y to equal 3, then x is greater than y. But x squared plus x is 2. So if we choose x to be 1, for example, so chosen x to be 1, so x squared is x squared, well, we've got the x squared plus x value here, which is 2. So 1 squared plus 1 is 2. And we've chosen y to be -3. Let's have a look at this, -3. So -3 squared plus -3 gives us 6. So x squared plus x is actually, in this situation, smaller than y squared plus y. So the statement is not true in the case where x equals 1 and y equals -3. So we've picked out 2 points where we can actually say, no, these two don't match up. You could have used other examples. You could use x being 1 and y being -4. You could have done x being 2, y being -4, but you get the idea. We want to find the quickest ones as an example. We don't need to show more than one counter example. We just need to show one counter example where we go, actually, no, this statement is not true because of this. And we've done proof by deduction, so let's go back and let's have a look by proof by exhaustion. So proof by exhaustion, let me go back actually. What we're going to do with proof by exhaustion is we're going to break the claim down into 2 or more cases, and we're going to show that it's true for every single case under consideration. So proof by exhaustion, our conjecture is to prove that there are exactly 4 prime numbers less than 10. So we need to evaluate basically all integers less than 10. So we're looking at all our numbers between 1 and 9. We're not dealing with negative numbers because we're talking about prime numbers here. So straight away, we can just forget about our negative integers here, because any negative integer has -1 as a factor. So we can just completely ignore all of our negative integers, and we're just dealing with our positive integers. So we're obviously less than 10, dealing with positive integers between 1 and 9. So 0 is not a prime number, as it is divisible by any number. 1 is not a prime, and here we go. So we're dealing with numbers between 1 and 9. 1 is not a prime number. We know that because it's divisible only by 1. 2 is a prime number. 4, 6, and 8 are not prime numbers. Straight away, we can say that because they're divisible by 2. So we've got rid of them. So actually, we've dealt with 1, 2, 4, 6, 8. Let's go to our next number, 3. 3, 5, and 7, yeah, they're prime numbers. So we've dealt with the numbers in between. 9's not a prime number, as 9's divisible by 3. So we've now split all of our numbers, that all of our integers between 1 and 9 into, are they a prime number, are they not? So we've gone 1, nope. 2, yep. 4, 6, 8, no. 3, 5, 7, yep. 9, no. Hence, 2, 3, 5, and 7 are the only prime numbers less than 10. So there are exactly 4 numbers less than 10. 4 prime numbers even less than 10. So that is one example. Oh, why can't I go back? There we go. That is one example of proof by exhaustion. And what we mean by exhaustion is actually we've gone through all the possible numbers, all the possible integers in between that would fit into this category. And we've gone through, is this prime? No. Is this a prime? Yes. Is this a prime? No. And we've said why it's a prime number as well. So we said 1's not a prime number because it's only divisible by 1. And then we've been able to say 4, 6, and 8 aren't because they are divisible by 2. as well as by themselves. Proof by exhaustion. So another example, we're going to prove that for any integer x, the value of fx equals x cubed plus x plus 1 is an odd integer. So we're going to split this into two cases, and then we're going to prove each by deduction. So case 1, x is an even integer. So x squared, so x will have to equal 2n for some integer n. So our integer is going to be 2n because we're saying it's an even integer. That's our notation for even integers. So therefore, f multiplied by 2n would equal 2n cubed plus 2n plus 1. If we're going to factorize that, we will then end up with 8n cubed, cubed, 8n cubed plus 2n plus 1. Therefore, we will get 2 multiplied by 4n cubed plus n plus 1. N is an integer. Therefore, 4n cubed plus n is an integer. Therefore, 2 lots of 4n cubed plus n is an even integer. Therefore, 2 lots of 4n cubed plus n plus 1 is an odd integer. So fx is odd when x is even. Case 2, we could have x being an odd integer. So in this case, x equals 2m plus 1. We're using m this time, as we've said before, because we're using two sets of integers that aren't related to each other. They have no relationship to each other. So we used n over there. This time we're using m, just so that we're not confusing it, because otherwise on the same question, if we're talking about n and m, we've already dealt with n being an even integer over there. We're going to want to talk about it now being an odd integer. So we're going to actually want to use another notation for integers. So we're going to use m instead. So this time x equals 2m plus 1 for some integer m. Therefore, we're going to rewrite the whole equation again. F equals 2m plus 1, which equals 2m plus 1 cubed plus 2m plus 1 plus 1. Then we're going to have it equals 8m cubed plus 12m squared plus 8m plus 3, which is 2 lots of 4m cubed plus 6m squared plus 4m plus 1 plus 1, multiplied by 2 plus 1. M is an integer, therefore 4m cubed plus 6m squared plus 4m plus 1 is an integer. 2 lots of 4m cubed plus 6m squared plus 4m plus 1 is an even integer. Therefore, 2 lots of 4m cubed plus 6m squared plus 4m plus 1 is an odd integer. So fx is odd when x is odd. So since fx is odd, both when x is odd and when x is even, and all integers are either odd or even, fx must be odd for any integer x. So this statement is true. And we're not going to do proof by contradiction, so I'm just going through now with you a couple more examples. So let me just minimize this. Let me find my next bit I want to go through. Here we go, exercise 1.1. Resume share. Okay. New share. There we go. Okay, so I've now shared this one. So basically, I'm just going to go through another set of proof examples for proof by deduction, proof by exhaustion, and disproof by contradiction. And then I will go through some examples for you to do. I will leave them on the end of this screen at the end of the video, and then I'll go through those answers next time. So if 2n produces a sequence, we would want to look at, so this is something for you to have to think about, what type of special sequence is this? So if n represents an integer value, what I would like you to do is to write down the expressions that represent the next two consecutive integers. So for example, if n represents an integer value, write down the expressions that represent the two integers either side of it. So we're going to look at direct proof or proof by induction. So we start with a given statement, our conjecture. We make a series of connected true statements, and then we confirm the results. So it's just a different way of looking at these examples. So I've done these in a couple of different ways for us to get used to seeing them explained differently. So direct proof. Prove that 3 is a prime number. So we've already had a direct proof. No, we had a proof by exhaustion with prime numbers. There's only 4 prime numbers. There's exactly 4 prime numbers and over 10. Now we've got a direct proof. Prove that 3 is a prime number. Okay, so our statement. Well, our statement is a prime number is a number that has exactly 2 factors, 1 and itself. We're going to show our workings out now. Well, 3 has exactly 2 factors, which are 1 and itself. There is no others. Our conclusion, therefore, 3 is a prime number. Another example. If you want, you could pause these, and then I'll go through the explanations now. So prove that the product of 2 consecutive numbers is always even. Again, we're talking about products, which means we are multiplying 2 consecutive numbers together. So proof by deduction, we're going to put our statement in. So we're going to let one number be n, and our consecutive number is going to be n plus 1 consecutive. And so if we carried on the sequence, it'd be n plus 1, n plus 2, n plus 3, blah, blah, blah. But we're just having n and n plus 1 for now. So our workings out. So if n is even, then n plus 1 will be odd, or vice versa. So it doesn't matter which way round we do this, but an odd number is always going to be multiplied with an even number. And so when an odd number is multiplied with an even number, it always gives an even product. Or we could say, show it in some algebra. Remembering that 2n means even, so 2n multiplied by 2n plus 1, so an even number multiplied by an odd number. This equals 4n squared plus 2n. Factorize that, we've got two lots of 2n squared plus n. So we're saying, look, this is an even number. If we've got 2n squared plus n, 2 times it's an even number. So we let 2n squared plus n equal k. Therefore, 2k is a multiple of 2, so it is an even number. So our conclusion is therefore the product of 2 consecutive numbers is always even. Another example, proof that the sum of 2 consecutive numbers is always odd. So this time, rather than it being a product, we've got the sum, so we're adding up 2 consecutive numbers together. Proof by deduction, we want our statement to start off with. We're going to let one number be n and its consecutive be n plus 1, same as before. You get used to this notation quite quickly the more you use it when we're talking about odds and even numbers. So our working out, so if n is even, then n plus 1 will be odd, or vice versa, it doesn't matter, and our pattern is always going to be that way when we're working for our numbers. So an odd number added with an even number will always give an odd outcome. So let's use some algebra to show this. N plus 1 equals 2n plus 1. 2n plus 1, by definition, this expression gives an odd number for any value of n. So 2n plus 1, doesn't matter what we have, we've got 2n, which would always give us an even number, but 2n plus 1 will always give us an odd number. Therefore, our conclusion, therefore, the sum of 2 consecutive numbers is always odd. Here are some questions. These are some great ones to pause and have a go at yourself. Prove that 1 is not a prime number. Prove that the sum of two consecutive odd numbers is always even. Prove that the product of two consecutive odd numbers is one less than a multiple of 4. Prove that the mean of 3 consecutive integers is equal to the middle number. So those first 4 are quite nice, easy ones that you should find that you're able to do quite quickly. The variations of ones that we've already done. 5 to 8, we're looking at things now like prove that the sum of the squares of 2 consecutive integers is odd. Hence, prove that the sum of the squares of 2 consecutive even integers is always a multiple of 4. So we're getting into a bit more complex when we need to do more multi-step processes. All the way up to 9 and 10, which are your hardest ones. So A and B are 2 numbers such that A equals B minus 2, and the sum and product of A and B are equal. Prove that neither A and B is an integer. So that is possibly the hardest one on here, or 10 is. They're probably both quite equally tricky. So if 5y squared is even for an integer y, prove that y must be even. Okay, so that was proof by deduction. We're going to have another look at proof by exhaustion now. So proof by exhaustion. It's simple. We're just going to check all our possibilities. And again, this is where we were using that table function. It's not necessarily always the most useful way to actually do everything all the time. So here is an example. Prove that the sequence given by 2n plus 1 produces only odd numbers. And we're going to do this for n being equal to or greater than 1 and n being equal to or less than 5. So we're going to check for all the possibilities that could present itself. So we're going to have n equaling 1. And we can actually work through this. We've only got 5 possible options here. So n equals 1, and so 2 times 1 plus 1 equals 3, odd. N equals 2. 2 times 2 plus 1 equals 5, odd. N equals 3. N times 2 times 3 plus 1 equals 7, odd. N equals 4. 2 times 4 plus 1 equals 9, odd number. And then finally, n equals 5. 2 times 5 plus 1 equals 11, odd. Therefore, all possibilities give an odd outcome, so the statement is true. In this situation, you have only got 5 calculations to do. It's example by exhaustion. We want to go through every possible answer and step, so actually you're just going to go through and do every single one of them. Here is another one of an example by exhaustion. We're going to prove that 2m is not divisible by 8 for all integers where m is greater than or equal to 1 and less than 4. M, I've got written there, I've actually got n written down at the bottom, which is a bit of a pain. As we said before, we can use m or n interchangeably if we're in one set of questions. Usually we should use n for integers. I've ended up putting m and n on, which is a bit bad, so ignore that. So I've put check for all possibilities, n equals, it should actually say m equals, or actually really at the top I should put 2n. So n equals 1. So 2 times 1 equals 2. Well, 2 is not a multiple or divisible of 8. N equals 2. 2 times 2 equals 4. Not a multiple or divisible of 8. And then finally, n equals 3. 2 times 3 equals 6, which is not a multiple or divisible of 8. We're not doing 4, remember, because it doesn't have the equals to symbol under our less than. So therefore, all possibilities give an odd outcome, so our statement is true. And finally, we're going to have a look at proof by contradiction one last time. So this is our counterexample one, sometimes called counterexample, sometimes called contradiction. So again, it's nice and simple. It's in the name. We find a counterexample. So example by contradiction. Prove that the statement, everyone in this room is a fan of Man United, is false. So you could ask loads of people. If someone in the room says, no, I'm not, I support Derby, I support Leicester, I support Liverpool. You go, oh yeah, well, so-and-so over there, they don't support Man U. So that's false. And that's basically what we're doing with proof by, well, disproof by contradiction. So prove or disprove the statement, all prime numbers are odd. Here we go. So prove by counterexample, contradiction, that the statement n squared plus n plus 1 is prime for all integers is false. So let's just pick a random one. Let n's going to be 4. Okay, so we're going to do 4 squared plus 4 plus 1. So 4 squared plus 4 plus 1 equals 21. Oh, okay, so 21 has more than 2 factors. Therefore, that is not a prime number. Therefore, the statement is false. And here we've got some more questions. So we've got 11 to 20 now, and these are a combination of our proof by contradiction or counterexample, depending on how you want to call it, and our proof by exhaustion. First two, really nice. So prove that there is only one square number and only one cube number between 20 and 30. Number 12, prove that if a month has 5 or more letters in its name, a 4-letter word can be made using those letters. That's again quite a nice one. 13, a trickier one. 14, quite nice again. 15, this is quite a good one actually. The product of two prime numbers is the product of two primes is always odd. Prove this is false. And so what you will often be given is, if it is proved by contradiction or disproved by counterexample, you'll often be told that you're going to prove that it's false. You're not just expected to just pluck out of thin air, oh, it's false. You're told to prove that it's false, and you need to actually find that example of when it's false. So that's quite a nice one for that. 16, when you throw two 6-sided dice, the total score shown is always greater than 6. Prove this is false. Another quite nice example, and then we'll get into some more complicated ones there. Let me just pause this screen share a minute. What we've got here, these would be some quite good ones to pause at and have a go at yourself as well, is these are a few more complicated proof questions. So these ones, you need to decide what method of proof you're going to use. So for example, P is a prime number and Q is an odd number. Sue says PQ is even, and Liz says that PQ is odd, and Graham says PQ could be either. Who is right? So what you need to do is you need to use a suitable method of proof to justify your answer. So you need to decide if you're using proof by exhaustion, disproof by counterexample, or proof by deduction to decide what you're going to do with those three, how you're going to prove, how you're actually going to decide that PQ, is it even, is it odd, or could it be either? So you need to choose a suitable method for proof for that and justify your answer. And that's part A for that. Then part B, Sue now says that P multiplied by Q plus 1 is always even. Is she correct? Use a suitable method of proof to justify your answer. You're not necessarily going to use the same method of proof here. Here, you've got a set statement. The first one, you've got an option of 3. So actually, you're going to have to decide which one is the true answer. It's going to be one of them 3 at the top. We've got the option of even, odd, or either. So it's going to be one of them. So possibly proof by deduction there. B, Sue now says that P multiplied by Q plus 1 is always even. Is she correct? You're probably realistically going to be looking at proof by deduction, possibly proof, more possibly realistically proof by exhaustion. But I don't want to tell you the answers here. I just want you to have a think. So yeah, have a go at them and then justify your answer. We've got use a suitable method of proof to show whether the statement any odd number between 90 and 100 is either a prime number or the product of only two prime numbers is true or false. So here, you're not being told to say that this is true. You're being asked to say, is this true? Is this false? So again, pick a suitable method of proof here. If we're being asked, is it true or is it false? Probably not looking for counterexample. Unless we've decided it's false, then you could use counterexample. But we've got, again, a range of values that we could be using. We've got a set range of values. So we've got numbers between 90 and 100. So we're just dealing with 10 numbers there. Pause the video again here to look at these questions. Use a suitable method of proof to prove that the value of 9n minus 1 is divisible by 8. So yeah, so these ones are a little bit more clearer on which type of proof you want to use. So 4, is it true that all triangles are obtuse? Use a suitable method of proof to justify your answer. Again, that might be one that you might want to use counter example. 5, prove that the sum of the interior angles of a convex hexagon is 720 degrees. And 6, a student says that all quadrilaterals with equal sides are squares. Use suitable method of proof to show if this statement is true or false. So again, you're not being told if it's true or false. You need to decide which one it is and use suitable method of proof to find that. And final, no, we've got 2 more sets of questions. We could pause here to look at these ones. Prove that the sum of the interior angles of a convex n-sided polygon is 180 n minus 2 degrees. 8, use a suitable method of proof to prove or disprove a statement. If m squared equals n squared, then m equals n. That's quite a nice one actually to work through. And again, you need to decide which form of proof you're going to use. 9, the hypotenuse of a right-angled triangle is 2s plus a centimeters, and one other side is 2s minus a centimeters. Use a suitable method of proof to show that the square of the remaining side is a multiple of 8. You're being told to show that it's a multiple of 8. So again, that's a clue at what type of proof that you might want to use. And the final 2, use suitable method of proof to show that n is greater than or equal to 1 and less than or equal to 5 in the set situation given below. I'm not going to try and read that out. It's easy for you to read it yourself. And then the final challenge, a teacher tells the class that any number is divisible by 3 if the sum of its digits is divisible by 3. Use a suitable method to prove this result for two-digit numbers. Again, you're being told to prove this result, so you are having again a bit of a clue given to you to what type of proof you should use. So let me pause this share again. Let me get rid of that and let me get this one back open. Screen sharing is start proof by exhaustion. Okay, so yeah, that is pretty much everything for proof at the moment. So we've got those 3 stages. What I would say is go through those questions, work through the examples that I've given. So pause the video, work through my examples, unpause the video, check your answers, check the strategies. There were 2 sort of different ways of working through them, and all the methods are exactly the same, but I've sort of explained them slightly differently, depending on how people quite like them. And then at the end of the second set, I've obviously got all those other questions that you can work through. So we've got the questions 1 to 10, and then questions 1 to 11, and then the mixed ones. So I think what would be really good is, Luna, please stop, is working through the questions specifically for proof by deduction, then the questions where you need to decide if it, then the questions for exhaustion and the questions for counter example. Then once you're really, really happy with working through proof on those 3 different types, then switching over and actually working through the questions where you need to decide what type of proof you use. It's really important actually with maths that you go and have a go at these questions, because there's only so much I can show you sort of an example, this is how you do it, but actually you need to get yourself familiar and used to using them. It's again using lots of your algebra from GCSE and working through the strategies yourself. So it is quite an independent topic and course really, A-level maths is. So whilst I can give you instructions and directions of where to go, and you can find loads of instructions and directions where to go if you do get stuck at any point, it is very much the onus on you to actually go away and work out and have a practice at these questions. Because it is more methodical and more following the pattern, it is quite important that you have a go at the questions yourself, because just knowing a few examples, they can be really wide and ranging for proof. So just knowing a few set examples doesn't necessarily mean that when you get around to an exam, you can actually answer the question. So actually having a good broad range of practicing through proof is really important. So yeah, so I will